Hello, welcome. My name's Adnan Hamid. I'm founder and CTO at Breker Verification Systems. I'm also vice chair of the test plan working group under the certification steering committee. So I tend to stand up here and talk to you from two sides, right? One as RVI and one as what Breker is doing. This presentation is about the certification concerns at the system level. So going past the CPU and the priv and unpriv spec to thinking about what you have to do for the advanced interrupt architecture, what you have to do for the IOMMUs. What does it really mean when you start thinking about atomics, acquire, release, CMO operations in the system context? This presentation is set up primarily as a tutorial as to what these issues are and what needs to be handled. And that's 80% of it, and 20% of it I'll tell you about what we're doing at Breker to solve these problems. So my overall structure is, let's talk a little bit about what are the problems in system-level certification. Then I'll spend the majority of my time sort of going into what does that really mean? What do these features do? How do they work? What are we trying to A, certify, B, verify? Because the fact is these specs, we have great specs, they have a lot of detail, but if you're coming into them from outside, they're really hard to understand. What's the basic idea? What's the big picture idea over here that the spec is telling you about? And this is our attempt to try to sort of explain some of that. Oh, what does this thing do? All go by itself. So that's the second point. Then we'll talk a little bit about how we are solving this problem with test suite synthesis. And then finally, I'll talk to you a little bit about debug and coverage, right, to finish it out. So in the certification steering committee, when we talk about certification, we sort of have these four phases in place, right? Microcontroller, apps processor, RVA23. But then we talk about phase 3 and phase 4, which is the SoC and the platform that the SoC is in, like, you know, consider a server platform. Damn, this thing is all on autoplay. Why did they do that? Give me just a second. I didn't do that, but somebody did that to my slides. Slideshow. Slideshow. Where's the thing that says use timing? Set up. Don't use timing. That's the most annoying thing. Okay. Pardon me for that. Okay, so yeah. So for the phase 2 and 3, right? It's all SoC level stuff. And if you look at the first 3 phases, really about ISA compatibility. The focus is on the unpriv spec, the priv spec, the things that we tend to spend a lot of time on. But as we go into the apps processor, we start thinking about the SoC, we start thinking about the platforms. It's much more a system integrity problem, right? It's not about the CPU, it's about all the things living around the CPU and how the system works. And of course, Breker is well known for doing lots of work in system verification. So the first motivation I'll talk about is atomics and memory consistency, right? So what are we talking about? Okay, we know and love our RISC-V hearts. We're all working very hard on this. If you're not, you shouldn't be in this conference, go away. And we spend a lot of time thinking about the unprivileged specification and the privileged specification, and this is all CPU-centric inside the core. But really, we don't plan to put one of these down, right? We plan to put n of these things down, right? That's what everybody is doing. Well, in the unpriv spec, unpriv, I think, we have atomics, we have acquire, release. You simply can't test them with one CPU, right? The whole conversation is, can 2 CPUs trade off access to that and to those bytes against each other? So you've got to worry about that in a system context. We have memory ordering rules. Again, if you have only one agent in the system, you can't tell whether ordering is violated. Cache coherency is a favorite topic of all system integrators, right? We're building very, very complicated caches, usually at least 3 level. Often the last level cache is distributed, which means it's sliced into pieces to go into some kind of a mesh architecture. Very complicated scenarios trying to make sure that coherency scenarios are met. It's all well and good, right? Actually, the RISC-V specification doesn't ever actually say cache, right? It just says memory consistency, and it talks about cache maintenance operations. So how do we get all of those right? Second motivation, this advanced interrupt architecture, right? This is not a CPU-oriented thing. This is a system-oriented thing. And the idea is, how do you get interrupts routed around in a big SoC? And the principle of operation is that you have this, there are two major pieces to the AIA. There's something called the IMSIC, the incoming message signaled interrupt controller. So message signal interrupt, what does it mean? It means that instead of, it used to be that when we had a system and you had a DMA that finished its operation, it would pull up some wire and this would be the interrupt going into the CPU. Well, when you have 50 uncore IPs and 16 cores in a system, this doesn't scale, right? So the idea of a message signal interrupt is instead you're going to do a memory write to a well-known address, and that's the thing that'll trigger the interrupt. So to pull this off, the AIA has kind of two major pieces. One is the IMSIC, and this is a piece that goes into every heart. Every CPU gets its own. Within the IMSIC, there are these idea of interrupt files. So there are multiple interrupt files, one for M, one for machine mode, one for supervisor mode, one for virtual supervisor mode. And they're all at well-known addresses. Okay? And then there's the second component, which is the APLIC, the Advanced Platform Level Interrupt Controller. Okay? And this is the guy who's really sitting out in the system and aggregating all the wired interrupts coming in from the DMAs and UARTs and whatnot, as well as all the external interrupts maybe coming across GPIO or whatever it is we're doing, right? So we can't throw away the old-fashioned interrupts, but we're trying to make them better. So this guy gets all the internal, external interrupts. And now that APLIC guy, the system architect now has choices. He can either set up the APLIC to do that MSI write into the IMSIC, so send it by a write into memory, or he can say, no, we're going to do wires anyway. And we're going to talk here in a second as to the trade-offs in those decisions. Okay, so that was interrupts. Next, let's talk about virtualization and memory protection. Okay, so looking at the privilege spec, we know about the MMUs, right? This is, we take virtual addresses, map them to physical addresses. I have an entire talk around this topic. And then we also have PMP, physical memory protection. So once you've mapped from the virtual address to the physical address, then you can say, okay, this heart is allowed to access these physical addresses. All about security. It's a beautiful thing. What happens when that memory request is coming up from the system, from a DMA, from a PCI Express? It is, the CPU is no longer in the way, and how do you protect memory in that case? How do you do virtualization in that case? And that leads to this idea of I/O bridges, where you have a so-called I/O MMU. It's all the same thing the CPU MMU does, but out in the system. Now, there is no CPU. You've got to reimagine how this whole thing works. And you have to have I/O PMP, right? This is not yet ratified, but it follows that if you have I/O MMU, you need I/O PMP, which is, again, doing the same thing, but he is guarding the requests coming from the fabric, not the requests coming from the CPU. Okay. And by the way, as you get into this, you'll realize that this I/O MMU has deep connections into PCI Express. PCI Express already has a feature called ATS, Address Translation Service. So the PCI guys figured out a long time ago that, hey, we got to deal with virtualization, and they can issue requests saying, hey, please give me the mapping of this virtual address, tell me the physical address, and I'll use it later on so you don't have to map every one of my requests, right? So these things, there's a lot going on that tie together. And I can see I'm going to run out of time. Okay. And then one last piece over here is debug and trace, right? So this is yet one more block that comes into the system. And this guy is there to give us hardware debug support, right? So this is the technology that when you're working with GDB and you set a breakpoint on a particular instruction, the hardware will give us a trap on that right instruction, or when you write to a particular location. This is the guy who deals with JTAG and so on. Okay. So my intention over there was to give you a quick run through what the various topics that are RISC-V specific system features that we all need to learn and know about. Now let me dive a little bit into what these things do. So, atomic memory ordering, right? What is the question on the table? Okay, you might have heart 0 come along to a memory access. You might have heart 1 competing for the same cache line. How does hardware decide who gets that memory? Meanwhile, maybe heart 4 is also doing that, and PCIe came along and said, oh, I also want that memory, okay? And we did all that while the DMA is also competing for the same address. So all these guys are competing for the same address. And how does hardware arbitrate? What happens if you're doing a bunch of accesses that are all trying to hit the same index in the cache? So while all this arbitration is going on, we just throw the line away, all right? So these are the concerns. Coherency verification, big topic. We've been working on this for 15 years, and we are far from done. There are many ways of approaching it. But one interesting strategy that was taught to us by a major customer is you go pick a set of interesting cache lines. Maybe interesting means go pick n cache lines that are all going to hit the same set index on one slice of the last level cache, right? And the point is that if it is call it a 16-way cache and you go get 50 of these addresses, then that cache is constantly having to dump a line every time a new line comes in. Okay. Having gotten these lines, you put some crosscuts on them. So the blue lines are maybe the first two. The blue is the first four lines of the cache. The yellow is maybe the 7th byte. And the green is maybe the last 2 bytes of the cache line. Whatever, some way of slicing it up. Then you put different agents to work on each of those slices. And importantly, those sets of agents are running in free-running loops. There's no synchronization across them. So what's happening is you're running these loops over and over again. Each time, you're getting a different timing case, right? You've got complex hardware arbitration, and we're trying to basically get the arbitration to screw up. And when you take these ideas and say, OK, the blue guys are going to do some sort of coherency pattern where you're trying to make sure that the right data is showing up on the right core. Meanwhile, the yellow guys are going to do some acquire-release ticketing system. So this is all about being aware of somebody else modified your line. And then the blue and the green guys are all doing some memory ordering litmus tests. And you're doing this in tight loops, putting the design under tremendous stress. This is how you break things, right? So these are interesting ways to acid test whether the systems are doing the right things. And when you measure this kind of thing and look at the traffic on buses, you get like just ridiculous amounts of coherency traffic running around as hardware desperately tries to keep up with what this poor test is trying to do, right? Okay. Let's talk about some of the use cases for AIA. So one use case of this IMSIC, right, the part that's associated with the CPU, is you can use them for inter-processor interrupts. In the multi-core system, you usually need some way for one CPU to poke another CPU and say, hey, go do something for me. And one way of implementing this is you have one CPU go right to the IMSIC of another CPU. Remember, the idea of the IMSIC is it's basically a memory mapped register file, right? A second use case is this IMSIC is designed with PCI Express in mind. So a PCI Express MSI, message signal interrupt, can go straight into a well-known address and generate an interrupt. We have to deal with all the other interrupts in the system, right? The less interesting ones. So things coming from DMAs, things coming from GPIO. And now you have this APLIC. APLIC could decide to communicate his interrupts through an MSI into the IMSIC. Or the system architect could say, no, I want to use a wire for this one. Okay? There are many choices for the system architect on what they want to do. Okay. So what's this idea over here? IMSIC, right? One per heart. There's a memory mapped structure of lots of information that you can configure and query on what's going on. And devices can indicate interrupts either with this message, the MSI, or with a wire. The good thing about this message signal interrupt is we're building high-performance NOCs that can send huge bandwidths of writes into memory. And we could have 50 agents all trying to get attention, and they'll go through, and it's very cool. What sucks about it is you cannot predict the latency of that interrupt. And real-time guys, right, for them it's not about I got to get it done fast. For them it's about I got to get it done on a precisely known amount. I don't care if the interrupt takes 10 cycles to make it. It's got to make it 10 cycles every time. 11 cycles, 9 cycles, no good. Okay, you can't do that with a message signal interrupt. Okay, I think I mentioned that you have different files for different privilege levels. Writes can come from other CPUs, can come from PCIe, from a DMA. And a little bit of an idea of what's in this memory map file, right? So this master enables some threshold idea of which interrupts should be passed. You can query it to see where interrupts are pending. You can enable different interrupts. Okay. The other half is this APLIC, and I truly am running out of time. This is the guy that collects the system interrupts and wires it up to the IMSIC. Again, he has his own data structure, and he has his own enables and delegation rules and so on. So I'm going to run past that a little bit. The IOMMU. So I'm short-circuiting a little bit over here, but he does all the page mapping coming in from PCI Express, coming in from the system. And finally, debug. He's the guy who helps hardware assisted debug over here, right? You can put breakpoints on instructions. You can put breakpoints on hitting particular addresses. This is all the logic that is with JTAG and so on, right? There's a special debug mode and so on. So what does Breker do to address these problems, right? I got to get through this part of it. So given systems like this, Breker is in the business of test suite synthesis. And the idea is we have some system VIP, a single source of truth that we have built that is fed to some synthesis tool. And he actually kicks out two things, right? One is a C program with embedded assembly. This is the thing that's compiled and run on the various CPUs. And the other is a so-called TBX file that's run by this TRECbox component, which is essentially a generalized trick box, right? It's a test bench component. And he can manage all the IOs for us. And this is how we're able to do all this testing of managing when interrupts or MSIs are triggered relative to what software is doing, so we can test all these cases. A little bit on these graph-based models. So let's talk IOMMU and page mapping, right? So there's some big graph. Some part of it you'll figure out where we are programming the leaf page table entry flags, something else on the non-leaf page table entry flags because they have different rules. Picking how the page table is structured, right? Which entries you're picking in the tables. Are you doing one level or two level hypervisor translation? What kind of operation you're doing, and which mode you're going to do it from. But the point I want to get you to is when you start thinking through all these possibilities in the graph, you end up with a search space of 10 to the 140, give or take, right? So a huge number of cases that can be covered, and the tool can go search these until you get tired of running any more tests. So what do one of these mapping IOMMU tests look like, right? So if you look into that, you'll see that in the test, we put in comments saying, yeah, here's the predicted page walk that hardware has to do, especially in the case of hypervisors. It's a very long set of accesses he needs to do. You'll see faults being injected at every stage of translation. You see the actual operation through virtualized address. You see there are funny rules for hypervisor on sign extension of your program counter, so we've got to manage that. Let's talk a little bit about AIA test cases, right? Oh, I have more time than I think I do. I see. Okay. So in an AIA test for these interrupts, coming into this, at the beginning of the test, the tool will go pick some randomized configuration for AIA, right? AIA, you saw those big memory mapped files. There are many, many ways to configure them, thousands, tens of thousands, maybe millions of ways. I actually haven't counted them yet. I should have a number for you, like 2 to the 140, 10 to the 140, I don't yet. But we pick some randomized configuration. Then in the test, right, we set up to predict the prediction of what we think will happen. We trigger the interrupt. In this case, we are having heart 0 send a interprocessor interrupt to heart 3 with a minor ID of 1F, right? This is, these message signal interrupts are nice in the sense that the interrupt source can inform the target, hey, here's why I'm interrupting you. So that makes it a lot nicer. Then, after we trigger the interrupt, we check to see that the interrupt was actually seen, right? So we actually wait until we get notification from heart 3's trap handler that, yeah, I saw that interrupt. If it's never seen, the test hangs. We do a bunch of other checks. Meanwhile, we're doing a storm of interrupts from all the other agents, right? So imagine that there are 50 interrupts running in the system all at the same time. And then at the end of the end of test, we're checking for spurious interrupts. So what's the thing with interrupts? When you trigger one, you want to make sure it was seen, all right, that it didn't get dropped. But there's a flip side, which is, and you want to make sure it was seen exactly once. That it wasn't seen twice, right? And yeah, okay, some people here are laughing, right? That is a common problem, that things trigger twice when they were supposed to trigger once. So we have an end of test check to make sure that there was no spurious interrupt that we kind of, since we weren't expecting it, we weren't checking for it, and make sure nobody fired when they shouldn't have. Okay. Let's talk a little bit about debug and coverage, and I'll be done. So debug. You start doing tests that have 4 cores, 16 cores. You're trying to fire, 30 interrupts in flight all at the same time while doing coherency scenarios, while doing IOMMU, and something breaks. Well, it's hard to debug who screwed up, right? It's hard to find where to look. So we have this idea of a debug tool that kind of gives you a holistic view of what the test is doing. In this case, we have 4 CPUs, 2 threads per CPU. Something fails, we'll show you exactly which task in the schedule failed. We'll tell you, okay, here are the memory addresses that are being used by that task. You get the failure right in this cockpit. We'll take you to exactly the line of code that signaled the error, and what it's allowing you to do is very quickly sort of come down to, okay, Heart 1 was unhappy on this operation because of this. Now, why did he think he was supposed to get that? And do you see all those arrows floating about in the schedule? That lets you to, and that tells you who was the guy who was providing the information for this task, right? Usually, debug isn't as simple as, oh, I'm going to look at 5 lines of code and find the problem, right? He was dependent on some other 5 lines of code somewhere in the test that caused this to break. So this is our debug idea. And then coverage. So I think it's not hard to convince you that for just page table walks, that there are 10 to the 140 possible cases, right? Once you multiply out all the different ways you can do page table entries and all the flags and all the modes, and you just keep multiplying powers of 2 and they go up really quickly, right? What to do about this? Okay, who wants to go write a coverage model to think about all of these? We don't. Instead, we go automatically generate all the possible paths through that graph, right? And we're asking the question, okay, has every path been exercised? It's a beautiful idea mathematically. Now, 10 to the 140 case. 140 paths are not that useful, so we have ways of filtering them to pick what we think are interesting. But it allows us to quickly think about the cross-coverage of many different concerns. And you get a picture like this, and the green paths say that they're done, and the red paths say, hey, I'm still waiting to have a test that exercises my particular scenario. And then to plug this all together, right, we are starting with the various ISA specs. So there's the core specs on priv, of course. There's the AIS spec, the IOMMU spec, the debug spec. We're up to eyeballs and specs. But we are linking those specs to our test plans, right? Which is saying, our test plans say, here's a strategy for how we're trying to test each of these. Our strategy is not the only strategy. It's just the one we picked. Is the strategy complete? By doing this kind of work, our customers will come beat us up all the time and say, okay, we like what you did with A, B, and C, but you forgot case D. Like, yes, sir, we forgot to say case D. We have to go fix that, right? And then that, of course, and then the test plans are tied into our graph models, so you can see exactly which of these cases were covered and not covered. Okay, so that's my talk. Do I have a little bit of time for questions?
We could probably get one question, but obviously people can find you out on the floor
I
as
refuse
well.
to talk to anybody who doesn't ask me a question in public.
Did we have a question?
Your debugger,
Let me catch you on the mic.
in real time, or are you doing it from a trace?
The question is the debugger running in real time, or am I doing it from a trace? The answer is, when we are running in simulation and emulation, we are running it in real time. When we're running in FPGA and post-silicon, we are slower than the platform, so we are post-processing. It's a good question. It's an important question, and it has implications like that tracing kind of idea will slow down a test, so we trace to memory and then dump at the end. But if you hung the system, we don't get the trace, so then you have to do the interactive trace, which may make your bug go away. So nothing's perfect, right? But at least we have all the, we've come through all of that work, right? So, yeah. I love it when people like you laugh because you know exactly what I'm talking about.
I'm just glad you're doing it, I don't have to.
Exactly. That's why we exist. Other questions?
Well, thank you,
Okay.
Adnan, and
Thank
thank
you
you
very
everybody
much.
for stopping by.